Okay, we stopped at the very start of this, I think, on Friday. And you two weren't here. You were here, yeah. All right, so this is where we were on Friday. Last time we were talking about, like, tuning the hyperparameters, but how do we go about doing that? And then once you've got your instance set, you've got your evolutionary algorithm, all of the symbolic and numeric hyperparameters are all set, and you hit run. And you get some result, great. And then you change it a little bit, let's say, and maybe you're saying, okay, I wrote a new crossover, and I think it's better, right? So you make the change, and you run it again. And maybe it's got better results, maybe it got worse results. I don't know. But how on earth do you actually even compare these things? Okay? Now, last time we were talking about with like tuning the hyperparameters. You're not really going to want to take this strategy when just tuning hyperparameters, okay? You're going to take this strategy when you want to demonstrate like, okay, this thing I did made a difference, for example. So yeah, like let's say I made a new algorithm, I made a new crossover, whatever. I want to show that something's better. How do I do that? All right? What you're not going to do is just hit run once and then hit run once and compare the numbers. That ain't going to work. And we know it's not going to work because the moment you hit run and then you hit run again with the exact same instance and you hit run again and you hit run again, you're going to get different numbers because of the random nature of what's going on, right? So it doesn't even matter. Like, so obviously you can't just compare run to run. It's not enough. So how do you actually compare these things effectively? Now, raise your hand if you've used p-values before. Yeah, okay, yep, good, good, good. Raise your hand, okay, keep your hands up. If you've used p-values, that's it, only 3 of you? All right, 4, okay. Now, keep your hand up if, keep it up. Keep your hand up if your understanding of the p-value is roughly the following. Well, it was less than 0.05, so I'm happy. Oh, okay, one person. Okay, good for you. The other, okay, good. Okay, yeah, cool. That's usually the understanding of what is going on when you're using p-values, which is horrible for scientists, okay? Now, I get it. Why is it that way? Because like often, like look, I don't know, no hate to the professors here. I didn't take stats here. But where I took stats, yeah, it was garbage. I didn't learn anything, right? So like it's not my fault I didn't know. It's the professor's fault, right? So what does a p-value really mean? What are we even doing when we're comparing these things? Now, here's my warning. I'm not a statistician. Everything I'm talking about is going to be kept at a high level, right? I'm going to skip a lot of formalisms, and I think that's going to be fine to give you the intuition about what on earth is actually going on when we are calculating these p-values and whatnot, okay? For the purpose of this course, this is going to be sufficient. If you want to know more, take more advanced statistics classes, okay? All right, so when you did a p-value before, let me guess, you did like a t-test? Does that sound right? Maybe you did like a Mann-Whitney U, which is similar, right? You know, p-values, right? And if it's less than 0.05, I'm happy. It's significantly different. But what does that mean? All right, so let's take a few steps back away from evolutionary computation. I am going to say a random variable is something that I can observe, okay? It's often represented as like a big X or something, but it's some arbitrary thing I can observe. Don't think of it as like a variable that you're used to in math, right? Where a variable is like f of x, right? Oh, x is the variable, x plus 1, right? Like, don't think of it like that. Think of the random variable as a thing I can observe. So often we're going to want to make this like quantitative measurement about this thing. Some examples would be like, okay, how long does it take people to recover from the flu? Okay, so the random variable would be like flu recovery times. The amount of nuts a squirrel buries in a day could be a random variable. The number of people with blonde hair that walk past this building between 10 to 11 on Tuesday, that's a random variable, okay? The best fitness value of an evolutionary computation run, a random variable, right? The idea is, whatever the measurement is, if I sit there and continue to record these things, like you can imagine, like who here's been sick before? Who here's been sick about the same time as somebody else? Right? And then like, did you recover faster or did they recover faster? Or did it take you the exact same amount of time to recover? Right? Obviously there's variation, obviously, right? So if I were to go and like if I were to infect everyone today, and I'd be like, how long does it take each of you to recover? The times are going to differ, right? If I go and observe a particular squirrel over the days, one day it might bury, I have no idea what a number of nuts squirrels bury a day is. So, but like, let's say like one day it buries 7, the next it buries 17, the day after that it's 7 again, and then 4, and then 11, right? It's going to be different every time. But the point is, I've got some random variable I'm representing as just a cube, okay? It's just a thing I can look at. And when I'm looking at it, it's spitting out these numbers. Boop, 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 right? And I can sit there and observe it as long as I want. And it's going to spit out all of these numbers, all right? And those numbers are part of a distribution. And if I were to plot that distribution as a histogram, I see something like that, okay? There is no special meaning behind any of these things at this stage other than there's some arbitrary random variable I can observe. It's spitting out some numbers, and because I don't love looking at just a column of numbers, I like to look at histograms because they help me out a little bit. So presumably, if I have observed this thing for a sufficiently large amount of time, I'm going to get a pretty darn representative distribution that is like what I could expect out of that box, right? Right? And, you know, I'll take a moment, like you've heard of things like confidence intervals before, right? That's all like about like the distribution of the data, right? Like if I know that this random variable is spitting out more information, and every time I just keep observing it, this distribution gets just bigger, like this way, but not like this way. It's telling me like, yeah, that distribution is really representative of like that thing, and so I can make some summary statistics about what's going on there, okay? But that's the idea. Any questions about this general idea? And please ask now, because it's only going to get more complicated. It's really not that bad, but it just is relatively more complex as we go. All right. So I could do it again. Here's some other random variable. You can tell it's different because it's a different shade of gray. And also because the data coming out of it looks a little different. All right? Now, I don't know how many times I hit run on this to generate this plot, right? But you look at this distribution and that distribution, and you look at them and be like, well, those distributions look different. Would you agree? Now, you could always play the question, did I observe it for long enough? Yeah, I don't know, right? But the point is, I think I've got a, yeah, cool. I've got these 2 random variables. I can have as many random variables as I want, and I can observe them. And remember, to just put this back in the context of evolutionary computation, this would be like an instance of an evolutionary algorithm. And remember, the word instance we use to describe it when everything's set and you're about to hit run. You hit run, you hit run, you hit run, you hit run, you hit run. You're not changing the number of generations, you're not changing anything. You're just hitting run. And you keep getting like, all those numbers are popping out. Maybe those are like best fitness values, I don't know. All right? We're going to get distributions. But again, to generalize it, it could be flu recovery times. It could be number of nuts buried, right? Whatever. Okay? Any questions? Usually, okay, so I'm observing squirrel A and squirrel B. Do squirrel A and B, do they bury like the same number of nuts, you know, roughly? Like that could be a question to ask, right? Or what about like if I give you, like all of you are sick, but I give half of you a new drug, right? Does it improve recovery time or is it basically the same, right? These are questions we might want to naturally start to ask. Or does my new crossover improve results? Okay? That's the idea. So going back to the flu recovery time, the random variables may be the recovery times of two different groups. One group has like a new prescription drug, the other group doesn't, right? And if I'm a big drug manufacturer, I want my like new drug, I want to show like, yeah, look, it halves the recovery time or something, right? So yeah, the random variables may be recovery times of two. Yeah, okay. Does one group recover faster? With the squirrels, does one squirrel bury more nuts in a day than the other? Does 1 year have more blonde people walking past the building on Tuesdays from 11 to 10? Does one evolutionary computation algorithm implementation perform better than the other? That's what we're looking for here, okay? I'm just setting the stage for the question. We can observe these things. These things are random variables. Basically, they're spitting out distributions of data. And the question is, are they different, right? Now, if every time you hit run, you got the same exact answer, right? If it did, like if you're hitting, if you got a deterministic algorithm, like Dijkstra's versus some other like pathfinding algorithm, right? And if one pathfinding algorithm is just like, if you're showing like it's always winning, right? There's no distribution. Every time you hit run, it gives you the same distance. It's better. It's better. How do you know? Because that number is better than that number, right? But here we have distributions. So it's hairy. How do you compare? So, for example, I plotted, here's the dark gray one, here's the light gray one. There's the distributions, and if I plot them on top of each other, this is just two distributions. I know if it looks like there's three, this is just where they're overlapped, right? Are these distributions different? The first thing you always want to do whenever you're asking this question is just do the eyeball test, okay? There's no need to jump to like, I need to do a t-test or something, right? Just do an eyeball test. What's an eyeball test? Look at it. Do they look different? Sometimes you get lucky and sometimes it's pretty darn obvious. Sometimes it's really not obvious and a lot of times you get something that looks like this where you're like, maybe, I don't know. Kind of looks like maybe orange is better, but I don't know. You see what I mean? Right? Better as in like maybe we want to minimize, right? So like, oh, that distribution looks like it's a little bit closer to 0 than the other one. See? And when I say like, oh, sometimes it's obvious, if you're plotting a distribution, if like one squirrel is burying this many nuts on average a day and another squirrel is like over here, it's burying way more, you don't need to do a t-test. You could be like, it's more. Why? Because it's, look at it. Like, assuming this is the same axes, right? Like, yeah, that one's doing more. How do you know? Right? Eyeball test, okay? But when you have situations like this, people are going to be like, try to like show me. How can you convince me? All right. When you look at these things, it does appear to be a little bit different, but there's a lot of things to take note here. Oh, there, I say right there. One, I only observed these random variables 50 times each. Maybe that really wasn't sufficient to capture what the distribution really looks like, because we like to think of these distributions as like n approaches infinity, let's say. The data's noisy. Right? There's, you know, it's just, there's always noise. Whenever you're observing anything real, there's going to be noise in the data. Now, the range of values obtained from each random variable. Okay, it's difficult to say if the random variable, it's really hard to say. And this is like the first example of like the framing we're going to do. Okay, this is how we're going to frame the question. And this might sound familiar to you. And I'll hit it a little harder once we get into the specific example of a drug trial. I do drug trial because it is the quintessential example of like what the hell this is all about. What we really want to know is, are these distributions different? Okay? I'm not even going to answer, is one better than the other? The key question I want to say is, are they different? Okay? All right, so it's able to say random variables are truly producing different distributions. Are they the same? Are these, like, could I have known, like here, for example, if you were to give me one data point from one distribution and another data point from the other distribution, I could tell you, like, if you give me a data point over here, I'm going to be like, oh, that was that squirrel. Why? Because it's clearly in that distribution. Or that was that squirrel. But if we go up to here and I say, like, well, here was one data point. Right? Like, yes, it looks like the distributions might be different, but if I gave you one more observation and said, oh, it's right here, could you say, is it from the orange one or the blue one? I would maybe, like, if I'm trying really hard, I could be like, probably the orange one, because we're really not that likely to get blue ones here. And it looks like, we're getting orange ones here, so, maybe. But could I really say? No. Hell, if I gave you one here, you're going to be like, oh, I have no idea, right? You don't know. So is the problem question clear? This is very important. All right, okay. They may effectively be the same. The two groups, so what would it mean if they're the same, right? So the two groups do not take different amount of time to recover from the flu. I gave one person the drug, or I give half the people the drug, the other half didn't get the drug, or maybe had like a placebo or something. And turns out there really is no difference. Maybe the two squirrels, there's really no difference between the number of nuts that they're burying. These ones, it looks like there are. But like maybe it doesn't even matter, right? There really isn't more blonde people on campus this year versus last year. Or the algorithm really isn't performing better than the next person's. Or like my new crossover really didn't make much of a difference, okay? Okay. So there we go. Now, how do we actually compare distributions? Well, we start with a very important assumption. And this assumption actually enables the whole thing. And it's not a bad assumption. It's not an assumption where it's like, well, you're assuming. No. You start with like an assumption called the null hypothesis. You hear that before? Null hypothesis, right? That means the null hypothesis is always going to start from the position of there's no difference. Let's assume there's no difference. But with that assumption, we get to make a lot of cool decisions, okay? And then we can demonstrate whether we're right or wrong. To be clear, you don't have to start from that assumption, but starting from that assumption, the framing makes the intuition a lot more clear about what on earth we're actually doing. I'm also, by the way, I don't know if I say this here. Yeah, okay. Yes, okay, all right, cool. So let's go with the example. The drug company, all right? We want to do a drug trial. A group of 50 people is given a new drug that's intended to reduce the recovery time of the flu, that would be wonderful, right? Wouldn't that be great? If you got the flu, here, take this pill, you will feel better faster. Great. Another group, though, is going to get a placebo. Now, and usually in these experiment designs when dealing with like people, a placebo is important because you want it to be like a blind trial where the people who are taking it don't know if they're getting the placebo or not, because that can actually have an effect. So it's a whole thing. So you give them a placebo and then you give the other people the real drug, and then you can do a comparison, right? You may have also heard of like double blind, where the people who are actually administering it don't know if it's a placebo or not either, right? So double blind is pretty common as well. Yeah, and often like all of the identifying personal information is like stripped before anyone's doing any analysis, right? Cool. All right, so another group is given a placebo, and so 50 people get the drug, 50 people get a placebo, let's say, right? No one in either group knows if they are given the new drug or the placebo. So here, the random variables are going to be the two unique groups. It's going to be, more specifically, the recovery time of the placebo group and the recovery time of the drug group. Even more specifically, it's like the number of like observable things. So I can get 50 data points from each effectively, right? Ideally you want more, but whatever, it's what we got. So yeah, further, the recovery time is itself a random variable. This is the property characteristic trying to be understood. All right, so let's say this is the two groups. All right, placebo group, drug group, okay? And when you do an eyeball test, if I'm like some big drug company, I can be like, yeah, see, it works, right? You can see, but everyone's going to say like, but does it really? That's the question. So with the above example, here's some summary statistics, stuff that you could just calculate based on the data. Really easy peasy. The average recovery time for the placebo group was roughly 15.4 days. The average recovery time for the drug group was 13.8 days. The drug group recovered, on average, 1.6 days faster than the placebo group. And with that basic summary statistic, you might say, it's better. It's better, right? But this would be a big mistake. Because, well, you'll see. All right, so one may be tempted to conclude that it's better. However, the average recovery time is a summary statistic of a distribution. In the distribution, there's a lot of information, okay? And what do you mean a lot of information? Look at that. Look at that. There's a lot of information. A summary statistic, one number, okay? So a summary statistic can't capture a lot of stuff. All right, okay, yeah, when observing the distributions, clearly there's more nuance, right? Case in point was that, like, if I give you this data point, like, what was it, 13.8? Let's say 13.8 is here. If I give you someone that's right on the average of the drug group's recovery time, 13.8, you look at that, yeah, you're not going to know what distribution it came from. You don't know, right? Even the 15 point whatever, you don't know. You really don't. So that's kind of what I mean with the nuance. There were only 50 observations from each group, right? I mean, these distributions might fill out if there were more and more observations. And every individual is different and every observation is different. If I were to do this again, let me put it, yeah. If I were to do this again, would you expect to see identical distributions? No, of course not. That's ridiculous. So, you know, it's noisy. And yeah, what are the odds? Here's the big question. What are the odds? Okay, I started it with, if I were to do this again, would the distributions look the same? Obviously not. Okay, so we concede that, like, okay, obviously not, right? What are the odds that this result just happened by chance? When I say result, I mean like these distributions. What are the odds that it just happened to look like this? You'll see what I mean by that very shortly, I think. Again, any questions up until this point? All right. All right, so we always start with what I was saying, that null hypothesis. And this allows us to ask this question, basically. Always assume there's no difference, okay? It's called the null hypothesis. It may feel like an arbitrary position to take, which it kind of ultimately is, but with that framing, it helps us follow this nice intuitive pathway into what the hell a p-value actually means. I'm also, by the way, you've probably done like t-tests, right? And you get the p-value with that. Now a t-test is a quick and dirty calculation to get like a p-value, okay? But really, the ultimate way you want to calculate a p-value is with something called a permutation test or a randomization test. Permutation test is better, I guess, but more on that when we get there. Okay, so These 5 points are magical. Listen very carefully and understand what I'm saying. Assume the drug, this is in the context of the drug trial. We're going to assume the drug has no impact on recovery time. That's the null hypothesis. All right, we already got that one covered. If the drug had no impact, then it could be expected that the average recovery time would be no different between the placebo than the drug one, right? The average recovery time, there should be no difference. If both groups had the placebo, it really would not have mattered which person was assigned to which group. Slow down. We're assuming there's no difference, meaning I might as well have given both groups the same placebo, okay? With the assumption that it makes no difference, okay? I know, you hear the word assumption, you're like, well, what if we don't want to make an assumption? We start by assuming this to frame the question, and then we will eventually check if our assumption was right or wrong, okay? And that's what the p-value gets us to, but we're getting there. But is that point clear? If the drug had no difference, I might as well have given both groups a placebo, right? And if I gave both groups the same placebo, would it have mattered who was in which group? Right? Imagine this room had 100 people in it, and I split them down the center. You got placebo A, placebo B, but they're the same, okay? Would it have mattered if I cut the room that way or cut the room that way in terms of seeing an effect? Probably not, right? It's the placebo. If it had no effect, it's not going to make a difference. So it should be possible to assign each individual and their corresponding recovery time, because each person is they go with their recovery time. If it made no difference, then it shouldn't have mattered which group they were in, right? So, if that's the case, the difference in the average recovery time between the two groups that were assigned would be an example of what one would get by dumb luck. Okay? Looking back at this, there's two distributions, okay? But I'm saying if we accept the null hypothesis, where there is no difference, and I split the room down like this, and I get this distribution, and then from over there, and this distribution's the blue one, right? But that should just be dumb luck, right? Assuming there's no difference, then this would be dumb luck, okay? So, assuming the null hypothesis, okay, if there's no difference, shuffle the groups. Take all 100 people, shuffle them, and put 50 of them over there and 50 of them over there, right? I don't care if they had the placebo group or not. I don't even care anymore because of the null hypothesis. It shouldn't matter. So I'm going to randomly assign 50 people to each group, regardless of if they actually got the drug or not, okay? I'm going to do that, and I'm going to, now, okay, shuffling the groups once and calculate the difference, okay? So technically, if there's no difference, this would be one example of a breakdown. I'm going to do it again, put everyone in a box, shake them up, and then split them. And then recovery time, recovery time, recovery time, recovery time, get that distribution, get that distribution. Recovery time, do it again, repeat, repeat, repeat. I'll get a new distribution every time. It's going to look a little bit different every time, right? Why? Because, well, we know it to expect that, right? Okay. So, okay. It is possible to generate all possible combinations of assigning 100 people to two groups. If all possible combinations are generated, all possible average by chance differences can be calculated, right? If I can generate every possible permutation of the 100 people into two groups of 50, and these are dumb luck things, then I can take the thing I want to check, average recovery time, okay? I could take, Put them in a box, shuffle, 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 average recovery time, average recovery time. Put them in a box, shuffle, 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 new average recovery time, average recovery time. Put them in a box, shuffle, 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 average recovery time, average recovery time. Okay? And we can calculate the difference between those average recovery times every time as well. You see what I mean? Right? So I do it x and x plus 1. Oh, okay, there's a difference of 1. X and x minus, oh, there's a difference of negative 1, right? Like, right? Okay. In fact, I can plot a distribution. Okay, okay, yeah. I could plot a distribution of the difference in average recovery times between the two groups, and it would look something like this. It's always going to look something like this. This is not a plot of a distribution like before. Before, it was individual recovery times from the two groups. Now what I've done is, assuming I could shuffle and randomize the groups some hilariously large number of times, which in the case of 100 people to two groups, there's 1.01 times 10 to the 29 combinations. There's a lot. But imagine we can do every single one, okay? I'm going to do every single one for the two groups and calculate their difference. Sometimes their difference is, a lot of time their difference is going to be around 0. Sometimes one group is like a whole day better. Sometimes a whole day worse. But, you know, as the further we get away from 0, the less likely we are to observe that. Okay? Yeah? Okay. So the point is, this is a very different distribution. It's a histogram. But before was individual recovery times from the random variables, where this is now like the difference in the group average recovery times. Which, by the way, the group average recovery times is the thing that we're kind of trying to evaluate. If they got the drug, their average recovery time is better. Often, by the way, so a permutation test, that means try every possible combination. If you could try every possible combination, do it. Realistically, that becomes impractical. So what you do is you just do some sufficiently large number of combinations. That's where like the randomization part. Permutation is, well, that's what you want. Randomization is like, okay, good enough, right? And if this is sufficiently large, it's not going to matter, okay? So there we go. What does this table mean? Distribution of, by chance, average group differences after 1,000 shuffles of two groups. Okay? This is the by chance difference in recovery times. Okay? Yeah? Yeah. I'm seeing, this is where I'm a little concerned, because the amount of vigor of the nodding went way down. What do I mean by chance? We are assuming the null hypothesis. We are assuming it didn't matter what group they were in. And if it didn't matter what group they're in, sometimes the people who just recovered faster went to that group, and the slower ones went to that group. And sometimes they went that way. Sometimes there's just a mix and mash of everything, right? So because of the null hypothesis, because we assume that there's no difference, this is the dumb luck distribution. By dumb luck, most of the time it's around 0. Sometimes by dumb luck, it's about a day faster, right? Other times it's a day slower, or whatever direction this goes. Doesn't really matter. Do you see what I mean? Now, here's the funny thing. I didn't, okay, what do I really want to show? Yeah, we start with the null hypothesis, right? But what do I really want to show? I want to show that, the drug actually made a difference, okay? And based on the groups that I had, this is the difference I observed, 1.6 days, okay? So, if I have 1,000,000 shuffles, how many, listen carefully, this is it. This is what this is all about. How many of the dumb luck differences are just as good or better than what I actually observed. So if we go here and do like 1.6 days, boom, that's the line. This is what the group that I actually assigned gives me. Okay? This is the dumb luck distribution. So, what is the probability that this happened by chance? That is the dumb luck. What is the probability this happened by dumb luck? That. That's what a p-value is. That's it. There's no more mysticism, right? It's like literally you say, assuming there's no difference, what would you get if you did this a bajillion times? And then, what did you actually get? And of those dumb luck ones, what proportion of them could happen by dumb freaking luck? Okay? So here, it has a 0.0205%. If this was real data, there is a 0.02% chance, or 1 in 50,000 chance, this happened by dumb luck. Okay? Meaning, I'm pretty happy. I would be very happy. Now, this does move on to another question, effect size, which is, well, how much of a difference did it make? Okay, yes, it made a difference, but do we care? That's a different question. But, yeah, cool. There we go. Only 205 of the 1 million could have landed there by dumb luck. And so we say, in this case, I would be like, well, what are the chances these are the same? The percentages? Imagine it was here or something, right? If the p-value was something like 50% or something, then you would say, why did I just lose my train of thought? If the p-value is really high, what are the chances happened by dumb luck? Oh, about 50% chance. Yeah, then the drug probably didn't have anything to do with the results, right? If half the time the dumb luck, you'd get this with dumb luck, well then we can't trust those results. But something like 1 in 50,000, we're pretty happy with that. Now, there's always that who here remember, they learned the alpha value. The alpha value is your cutoff, right? It's 0.05. You want to beat 0.05, okay? This beat 0.0002, so we're happy. But 0.05, right? That means there's a 1 in 20 chance. Let's say, okay. Who here has okay. Let me finish this and I'll go on to explain. Okay, realistically, what you want to do is a permutation test. But let's say it's the year, okay, when did t-test show up? Let's say it's the year 1900, okay, and you work at the Guinness Brewery and you want to do some stats on beer, okay? Which is really where this came from, by the way, which is pretty cool, right? And you're looking at how many combinations do I have? How do I demonstrate that there's a difference, right? How many combinations do I have to do? That poor guy, whatever their name was, is going to be sitting there with a piece of paper, writing out numbers, calculating crap for a bajillion years. And then they were like, actually, wait, we could actually come up with a quick and dirty way to get a p-value, okay? And they did that's the t-test, all right? A t-test, it makes several assumptions that allows you to do a calculation by hand pretty quickly without having to do this. You could probably tell by this description, it's a very algorithmic process, a permutation test or randomization test. To me, when I learned this, I'm like, okay, you put in a for loop, save the result, right? It's a very algorithmic heavy, where the t-test, it's a closed form calculation, you get your number, right? So you can get it quick and dirty. Chances are, now fortunately today we got computers, right? But if it's 120 years ago, yeah, you ain't doing a million examples of shuffles, right? You're not doing that. It's not realistic. So something like a t-test is good. But today, things like actually doing the permutation test is not a bad choice. And what's nice about a permutation test is you can test whatever the hell you want, right? Where with t-tests and whatnot. But anyways, long story short, you really want to do a t-test, right? And that's like what the p-values are from, but a permutation test. But if you did a t-test or Mann-Whitney-U, it's fine, right? But now you know what a p-value is actually telling you. I also told you there is a thing called like effect size. I think I talked about this a little bit before when we did one of the like examples. I think like the N Queens one or something. Effect size is like, okay, yes, it made a difference. Yes, it is. There you go. Look at these distributions. And the difference of 1.6 days seems to be real. And like there is a difference, okay? If this drug cost $5, then like awesome, right? Like yeah, 1.6 days, fantastic. If that drug cost $5 million, we might say like, well, yes, it's different. Yes, it's better. Is it worth it? I don't know, right? So effect size, so comparing the distributions just tells you if they're different, where you would want to do like an effect calculation to get a sense of like, well, how different is it? That's important, okay? And there's a couple of quick and dirty ways to do that as well. Just load up scipy.stats. There, you got everything you could need. Another thing too, so I was talking about 0.05, right? If 0.05 is the alpha value, that literally means there's a 1 in 20 chance that we got this by dumb luck. That's what it would mean. A p-value, if you had a p-value of 0.05, that means that if you took 100 papers, you would expect 5 of them to be bullshit. They didn't do anything wrong. It's just that's what the p-value tells you. It's funny. In certain disciplines, they don't even report p-values. They'll be like, we beat p-value of 0.05, right? And then who here's heard the phrase like p-hacking before? P-hacking is this idea where like, look, if you really want, it's really easy to cheese your like stats to get whatever p-value you want. It's just straight up lying, right? It's lying with extra steps, but it's lying, okay? And why do they want to lie? Why do scientists want to lie? Why is it that if you go plot of all p-values in papers, why can't I find what I'm looking for? This might be it. If you were to, look, basically, I don't know why I can't find it right now. If you were to look at like a plot of like research finding p-values, right? You get and then you get a weird bump around there. Why? You would assume a nice uniform, or something kind of like a more uniform distribution of p-values that you get in your results. So why does it look like this? Well, because of psychology. Well, there's that as well. Psych is particularly bad for this. But yeah, I'm not going to be that mean. I'm being recorded. Basically what it means is, if I'm a scientist, I need to publish my work. And if I need to publish my work, I need to get good results. So I'm just going to say I got good results, right? And all I have to do is get a p-value of like, oh, it was 0.48 or 0.048. Oh, that's significant, right? So everyone's p-values, like they don't want to lie too much because then it's obvious, right? They're going to lie just a little bit. And sometimes it'll be on either side because sometimes you want to show things aren't different when they are or something, right? So p-hacking is a real big problem. And on top of it, even with p-hacking, there's a good chance, like there's a 1 in 20 chance that you're like that. A paper that says there is a difference. This drug improves recovery times. That squirrel buries more nuts. Whatever it is, if you only care about 0.05, there's a 1 in 20 chance. It's nonsense, which is really bad in my opinion. For me, my philosophy is tell me the p-value. Just tell me what it is, okay? Don't tell me if you beat 0.05. If you get a p-value of times 10 to the negative 7, okay, it's different, right? 0.05, okay. And who picked 0.05 anyway? Who picked 0.05 anyway? Oh my gosh, come on. Generate, no, alpha value. In 1925, he chose the value partly because it was a convenient cutoff that corresponded to approximately twice the standard deviation in the normal distribution. And here we are, right? There was method to the madness, I guess, but we just kind of stuck with it. And also, you want to know something bad too? Everyone who's doing this p-hacking, I would say like the overwhelming majority of people whose papers that you read and it's published and everything, and they're reporting p-values, they have no idea what the hell that means. They just know that, oh, the number's less than it's good. I got the numbers I wanted. They passed that threshold. But at the end of the day, they probably don't even really understand what's going on. So this lecture is to show you, okay, this is what it means. If you're doing a t-test or a Mann-Whitney U, it's a quick and dirty calculation for doing something like a permutation test, right? It's not going to give you the full thing, so don't be surprised if you do a full permutation test and you start to get wildly different results, but it's still going to give you like the idea because you can calculate it like that as opposed to however long it takes to run a million simulations or something, right? Any questions about that? So that's a p-value. It all starts with, this is the dumb luck distribution. This is all, imagine I actually generated every single possible permutation, times 10 to the, what was it? So times 10 to the 29, right? But let's pretend I did. That means I have every possible dumb luck, every possible group difference there is, right? And if we assume that there's no difference, then all of those are the dumb luck differences, but what did I actually observe? And how many of the dumb luck ones were better than that? Yeah. You can never have a p-value of 0, really, right? Because it would at least have to be 1 over the number of permutations. Because what's the odds of it happening by dumb luck? Well, the one you observed could have happened by dumb luck. Even if it's the most extreme one, it could have. So it's always going to be like 1 over the number of possible, but nevertheless. Questions, thoughts, concerns, comments, anything else?
It's kind of a general question, but I'm just curious, could you, like, how would you compare two distributions that have the same mean, but one's much narrower? Like where one, you're more likely to get a better value, but also more likely to get a worse value? So maybe it's just...
Well, I would imagine if the distributions actually look that different, you're starting with an eyeball test, and you're going to be like, ooh, they look pretty different. But you could still do a permutation test to do the exact same thing, because if it is way different, I know if you're saying like, well, the mean, right? Maybe the average is kind of eat it out there, right? But you could also use like a p-value, or sorry, a permutation test to like test any summary statistic you want. So you could be like what is the confidence interval of these things? What's the difference in the confidence interval? And so like you can use this strategy to compare anything you want, right? Yeah. All right. I think we'll call it there for today. Well done, everybody.